I was travelling in the United States and I had been reading about the field of brain-machine interfaces that was developing. The organisation that was conducting this work is DARPA, the Defence Advanced Research Projects Agency, which is world-renowned for developing radical, innovative research. Essentially what we're trying to build is a bionic spinal cord. The challenge for us with this technology was partly that we were not familiar with what the brain signals would look like when you're recording brain activity from inside a blood vessel in the head. There is other research groups out there who are achieving brain recordings for the purpose of brain-machine interfaces by taking off the skull in an operation called a craniotomy, by injecting electrodes directly into the brain and then recording activity from the part of the brain that enables movement. Those brain signals associated with movement are translated through a computer with the use of an algorithm, and the signal out of the brain through the computer is then fed back into a robotic limb or a mobility assist system such as an exoskeleton, which enables the user to control that system by a direct thought. The step we've taken is in avoiding the open brain surgery step and delivering our technology without having to conduct any open brain surgery.
So this iteration of the device is designed at returning mobility to people with paralysis. The device has gone through a number of iterations. There have been a large number of challenges that we've had to overcome to manufacture a device that's suitable and safe for implantation. One of the main challenges was to enable a device that was flexible enough to get around the blood vessels, as well as strong enough to be pushed through the tube required to deliver it. The device is made out of nitinol, a nickel titanium composite that enables it greater resilience when being flexed and compressed over other more commonly used materials, which allows us to deploy it through a very small catheter and expand it to a larger size when in the blood vessel region of interest. Engineers always want to put more bells and whistles on things, and clinicians like things to be a lot easier, and we've been able to meet halfway, and so this device is quite simple for what it can achieve.
We've managed to develop the technique to implant this device and record activity from the motor cortex in the brain. The device is put in through a very superficial cut. Using a fluoroscope, this is a device that we can watch the path of the catheter travelling up through different blood vessels into the brain. We can navigate the device up into the brain. We put it into a blood vessel called the sagittal sinus. This is in the middle of the brain. It sits on top of the motor cortex, and the device sits within the blood vessel. The device has electrodes around the outside, and these electrodes pick up the nerve activity from the motor cortex in the brain. And the aim, as I mentioned, will be to take these signals and use it to move a bionic limb or perhaps even a wheelchair in people who have paralysis.
This is a fantastic story from Melbourne. It really shows the wonderful advantage of the Parkville precinct, where we have the collaboration and the infrastructure of the University, of the Royal Melbourne Hospital, and of the medical research institutes, in this case particularly the Florey Neuroscience Institute. This has been a holy grail for the research in bionics, is to develop a device to record brainwave activity over a long period of time, and mostly it's been done by implanting directly through neurosurgical procedures electrodes onto the brain. The problem with that is it is invasive, it has risks, and also the electrodes are planted directly on the brain can set up infection and fibrosis, and ultimately the quality of the recording deteriorates. Where inside the blood vessel it's much more protected and able to be and it doesn't damage the brain in any way, and able to be kept there long term. So it provides a new method by which we can achieve what people have been trying to do for a long time.